We are Team 13, and this is our IA2 for the subject BVLSI. The topic for given to us is 4-bit CLA adder using CMOS mirror logic using LTspice software. All our circuit would be simulated on LTspice. Uh, for the expression and equations part, my teammate Dinesh would be explaining these.
So here are the generalized term for generate term, propagate term, carry term, and sum term. The generalized equation for generate term is AI and BI. For propagate term it is AI or BI. For carry it is CI plus 1 is equals to GI plus CI and PI. For sum, SI is equals to GI and CI or CI plus 1 bar into PI plus CI. So this is the carry all equations. There are four carry equations that is from C1 to C4. If we substitute in the generalized equation of carry, then we will be getting these four equations from C1 to C4. This is the truth table for full adder. For the generate term, it is A and B. So if both the inputs A and B are 1, then the generate term will be 1. So that's why the last two combination it is 1. For the propagate term, it is A or B. If any one of the input that is A and B is 1, then the propagate term will be 1. For the carry out equation, it is G plus C in into P. Uh, for the combination in which 0, 1, 1, it is 1. For the combination 1, 0, 1, 1, 1, 0, and triple 1, the carry out term is 1. So the LTspice implementation will be explained by my teammate Lakshya.
So here we can see these are all our generate terms. First, let me see how a single generate term is implemented. For G0, we have implemented it using static CMOS logic. Uh, for the NMOS part, we have implemented a basic AND gate that is AI and BI. Here you can see A0 and B0 are connected in a AND configuration in the pull down network. And for the pull up at network, we have implemented a PMOS in an OR simplification which is generally inverse of the pull down network. And for the NOT gate, we have to get the G0 from the G0 bar, we have implemented an inverter using static CMOS logic. Similarly, for the propagate terms, we have also implemented the propagate terms using static CMOS logic. We have implemented the pull down network using basic OR gate and the pull up network using basic AND gate and connected an inverter at the output. For the sum terms, we have used mirror logic as mirror logic follows duality principle. Here you can see both our circuits look similar for the pull up and the pull down network. The only difference is the P0 and G0 terms interchange their positions for the pull up network. And a inverter is connected at the output of this network to get S0. These are all our sum terms. Similarly, for the carry terms, also the CMOS mirror logic is used. Pull up and pull down networks are mirror of each other, but T0 and V0 interchange their positions. These are all our carry terms. For the LTspice simulation and waveforms would be presented by my teammate Vipul.
So these are our LTspice circuits. These are the input terms that we have given. These are the generate terms, and these are the propagate terms that we have given for the circuit. These are the circuits for carry terms. and these are the circuits for sum terms. This is our dot model statement that we have given for PMOS and NMOS. For NMOS, uh, the threshold voltage is 0.7, the channel width is 16U, and channel length is 2U. Kp is 50U. The Kp for NMOS is double of PMOS, and channel width is also double of PMOS. For PMOS, VTO is 0.7, channel width is 8U, channel length is 2U, and Kp is 25U. We have run this for 10 milliseconds. This is the simulation result that we get after running our circuits. As you can see, from 0 to 1 millisecond, the input that we have given is 1000 and 0000. So the output that we should be receiving is 1000 and the carry should be 0, and which that is what the result we have achieved here. Now further examples and the working of the summing circuit will be explained by my friend Shruti.
Okay, so as we have gone through the circuit designing, now let's cross-check our output waveforms with this expression as we can see of a 4-bit CLA adder where we are performing the addition of two 4-bit binary numbers which are A3, A2, A1 and A0 and B3, B2, B1, B0. The carry terms generated here are C0, C1, C2, C3 and C4, and the sum terms are S0, S1, S2 and S3. So now taking our first example, which is between the time period 0 to 0.6 milliseconds. Here our A3, A2, A1 and A0 terms are 0, 1, 0, 0. And our B3, B2, B1 and B0 terms are 0, 0, 0 and 0. So the output we get, which is our sum terms over here, S3, S2, S1 and S0 are 0, 1, 0, 0, and the C4 and C0 terms are 0 and 0. So we can verify this from our waveforms as well, where we can clearly see that the terms which we have got are same in the waveform as well. Going to our next example, where our A3, A2, A1 and A0 terms are 0, 0, 0 and 1, and our B3, B2, B1 and B0 terms are 0, 0, 0, 0. Here also we get our sum terms same as that in the waveform, which is S3, S2, S1 and S0 are 0, 0, 0 and 1, and our C0 and C4 terms are 0 and 0. This was between the time period 2 to 2.2 milliseconds. Now seeing the next example where the time period is between 4 to 4.4 milliseconds, our A1, A2, A3 and A0 terms are 1011, and our B3, B2, B1 and B0 terms are 1101. Here are some terms S3, S2, S1 and S0 are 1000. Our C0 term is 0 and our C4 term is 1. So that we can clearly see. So thus we have verified the circuit as well as the waveforms. This circuit is a huge circuit consisting of 162 transistors, and they all work together to give us the addition of two 4-bit binary numbers. Hence, our circuit of 4-bit CLA adder using CMOS logic, mirror logic works perfectly. Thank you.